I'm Jonathan, and today I'm going to be teaching you the basics about vectors. So first of all, when we're going to be adding two vectors, we're going to call this vector over here u, and we're going to call the vector on the right v. Now if we're going to be adding these two vectors, what we're going to be doing is adding across. So we're going to say 2 plus 1, we're going to say 1 plus 4, and then 3 plus 6. Now to get our final result, we're going to just add all of these things here up. 2 plus 1 is 3, 1 plus 4 is 5, and 3 plus 6, that's 9. Now it's very important that when you add vectors, you ensure that the two vectors are in the same form. We started off with 3 things in each of these vectors, and we ended up with 3 numbers in our final vector as well. It's not possible for you to add vectors if they have a different amount of elements in them. So if I had a vector like this, 1, 2, 3, 6, it would be impossible for me to add that to a vector 1, 2, 3 because these two vectors have a different amount of elements in them. Now we're going to move on to our next example of addition. If we add these two vectors, we're going to say 2 plus minus 1, and that's going to be 2 minus 1, which is 1. 1 plus 2, and that's 3, and then 3 minus 4, and that's going to be minus 1. Next, we're going to be moving on to subtracting vectors. If we have these two vectors over here, one thing that you need to pay attention to is the negative sign that we have, because if you're subtracting a negative value, then you're going to be having two negative signs. So 2 subtracting minus 1 from it, and that's going to be 2 plus 1, which is 3. We have 1 minus 2, and that's going to be minus 1, and then 3 minus minus 4, and that's going to be 3 plus 4, which is 7. The next important part of vectors is multiplication by scalars. Now when we multiply by scalars, we're going to be multiplying each number inside our vector by the thing on the outside. So it's going to be 3 by 2, that's going to be 6, 3 by 5, 15, and 3 by 7, which is 21. Again, this is going to be in the same form as the vector that we have, 3 elements in the starting vector, so we're going to have 3 elements in our final vector. Our next example, minus 5 by 2, negative 10, minus 5 by minus 6, that's going to be a positive 30, and then minus 5 by 4, which is minus 20. Now, dot product is a different kind of multiplication with vectors. When we multiply to find the dot product, we're going to be multiplying these values and then adding the sum of each pair. So we're going to start off with 1 multiplied by 3, 2 multiplied by 1, and 4 multiplied by 4. And we're going to be adding all of these products. So 1 by 3 is 3, plus 2 by 1, which is 2, plus 4 by 4, which is 16. And that gives us 18 plus 3, which is 21. Now for this other vector down here, minus 7 by minus 2 is going to be 14, plus 3 by 8, which is 24, plus 4 by 1, which is 4. Now I'm going to actually get my calculator for this one here. 14 plus 24 plus 4 is going to be 42. Now the equality of vectors. For two vectors to be equal, that means that each element is going to be equal to the element in the other vector. So in this case, x is going to be equal to 2, y is going to be equal to 5, and 7 is going to be equal to z. Now, sometimes we use this kind of equality of vectors to give more complicated questions. So in this example, you could be asked to find the values of x, y, and z. Now, how we do this is by equating these two vectors. Now, 5 is equal to x, which means that x is equal to 5. 3 is equal to y minus 2. We're going to be adding 2 on both sides, and that means that y is equal to 3 plus 2, which is 5. And for this one, we're going to be saying that c plus 3 is equivalent to 2. So c plus 3 is equal to 2. Now to get rid of this 3, we're going to be taking away 3 on both sides. I'm going to say that c is equal to 2 minus 3, which means z is equal to minus 1. So that's how you'd find the values of x, y, and z if you were told that these two vectors were equal. Now, the magnitude of vectors, and this is a next very important topic. If we have a vector u with the values 1, 2, and minus 2, if we want to find the magnitude of this vector, what we're going to be doing is adding the squares of each element inside the set. So to find the magnitude of this, first of all, the notation for magnitude of a vector is 2 straight lines on the side of it. So the vector here was u. This is going to be the magnitude of u. So the magnitude of u is going to be equal to the square roots of 1 squared plus 2 squared plus minus 2 squared. That is going to be the square root of 1 plus 4 plus 4, and that's going to be the square root of 9, and the square root of 9 is 3. Now, the magnitude of vectors is very important because we can use this to find out whether or not a vector is a unit vector. If the magnitude of a vector is equal to 1, then that vector is a unit vector. So we have v, and we're going to be letting v be equal to the vector 1, 0, 0. Now the magnitude of this is going to be the sum of all of these elements squared. So it's going to be 1 squared plus 0 squared plus 0 squared. And that's going to be the square root of 1, which is 1, and so v is a unit vector. A vector over its magnitude is always going to be equal to a unit vector, and that simply means that the magnitude would be equal to 1. So I'm going to be showing you an example because that sounds extremely complicated on paper. Now if I have a vector v which is equal to x, y, and z, we're going to find the magnitude of this vector. It's going to be the square root of x squared, that's the first element, y squared plus z squared. Now if I put v over its magnitude, that's going to look something like this. We're going to put x, which is the first element, over the magnitude, which is the square root of x squared plus y squared plus z squared. We're going to put y over its magnitude, and that's going to be y over the square root of x squared plus y squared plus z squared. We're going to put z over the magnitude, and that's going to be z over the square root of x squared plus y squared plus z squared. Now if we find the magnitude of this vector, again we're going to be taking these elements. Now this can get a little bit confusing, but I'm going to be drawing a circle around the element so that you can follow what I'm doing here. So we're going to be adding the first one. So we're going to say x over the square root of x squared plus y squared plus z squared, and we're going to be squaring all of this because we squared the element and we put the square roots of the sum of them. So you're going to put the second one. The second element here is going to be this. So you're going to say y all over the square root of x squared plus y squared plus z squared. And you're going to be squaring this as well. And you're going to put this, the last element of the set here, of the vector, and that's going to be z over the square root of x squared plus y squared plus z squared, and you're going to square all of this. Now when we square all of the values, what we end up with is x squared because you have to square the denominator as well. But when you square a square root, you end up with the thing itself. So we're going to get x squared plus y squared plus z squared plus, we square both things here, it's going to be y squared over x squared plus y squared plus z squared as well. And then we're going to look at the last one as well, and that's going to be z squared over x squared plus y squared plus z squared. Now, if you look at these three things closely, what you realize is that they have the same denominator, which means that we can add the three values on top and just keep the common denominator. So I'm going to be adding the three of those. I'm going to get x squared plus y squared plus z squared all over x squared, which is the denominator, plus y squared plus z squared. And coincidentally, this is the same thing. So this is going to be 1 over 1 because everything cancels. And that proves that it is a unit vector because the magnitude of v over its magnitude is equal to 1. Now I'm going to be explaining something I think is very, very important to understand. Now, on the Cartesian plane, we have x and y axes. We can only go left or right or up and down. This is what we usually use in school to draw normal graphs. And what I want to show you is that if we have some coordinates 2 and 3, all of our coordinates are always in relation to the origin. So if we have 2 on the x-axis, we know that we are supposed to go 2 away from the origin, and then if it's 3 on the y-axis, we know that we're supposed to go 1, 2, 3 on the y-axis, 3 away from the origin. So that point would be somewhere about here. Now, when we are working with 3 dimensions, it's very similar. But the difference is that in 3 dimensions, our vectors have direction as well as a magnitude. So if I have a point A and a point B, if I say that the coordinates for the point A are 1, 2, 3, then this is going to be in relation to the origin. So instead of just saying A, I could also say OA if O is the origin. Now, OA would be equal to 1, 2, 3. If I want to get from A to point B, however, then I want to go from A to O and from O to B. So to go AB, I would just put a little bit arrow over here. This is the standard notation for vectors. We usually put an arrow. So to get AB, we have to go from A to O, and then we have to go from O to B. Now, if I go from A to O, I'm no longer going from the origin to some points 1, 2, 3. I'm now going from 1, 2, 3 to the origin, which is 0, 0, 0. Now, because vectors have direction, the point AO is actually going to be equal to -1, -2, -3. And that's because I'm going from these points right here to 0. So I'm actually subtracting. Now, you realize that OA and AO have the same values in them, but the signs have changed. But if you really look at it, if I wanted to get from OA to change this to AO, all I'd have to do is add negative values to all of it. I'd just be able to multiply through by -1. So what we can actually do is say that negative OA is equal to -1, -2, -3. And because this is equal to AO, instead of writing that AB is equal to AO plus OB, we can switch out AO for negative OA. So that's going to look something like this. AB is equal to minus OA plus OB. But when we work with vectors, we usually like to put the positive thing in the front. And so instead of writing it this way, it's going to be the same thing, but we're just going to be changing the order of it. So we're going to say that AB, in the arrow, which is the common notation, is equal to OB minus OA. So this question asks us to find a unit vector in the direction of PQ, where OP is equal to 3, 2, negative 1, and OQ is equal to 4, 2, 1. Now, to get PQ, we're going to be following what we did for AB. So what I usually use is this little trick, and whatever is on the outside, I make sure that it stays on the outside, and then I put O in between them. So we're going to say PO plus OQ, and that's in the same style as AO plus OB to get AB. So PO plus OQ is equal to PQ. But for the same thing that we did for AB, we're going to do it here. Instead of writing that, we can put OQ minus OP. Now, when we look over at the question, we realize that we do actually have OP and OQ. So PQ is equal to OQ, which is 4, 2, 1, minus OP, which is 3, 2, negative 1. Now 4 minus 3 is 1, 2 minus 2, that's 0, and 1 minus 1, make sure you pay attention to the negative signs, that's going to be 1 plus 1, which is actually 2. Now we know that to find a unit vector, we need to put that vector over its magnitude. So if we're going to put this vector over its magnitude, we have to actually find the magnitude of that vector to begin with. So the magnitude of this is going to be 1 squared plus 0 squared plus 2 squared. And then we're going to square root all of that. And that's going to be equal to the square root of 5. Now, when we have some kind of fraction, right? If we have 3 and we want to divide by 5, for example, this is going to be equal to 3 over 5. But also, if we have 3 and we multiply by 1 over 5, because 3 is equal to 3 over 1, we're actually still going to end up with 3/5. So instead of having to divide by root of 5, we can actually multiply PQ, which is 102, by 1 over root 5 using scalar multiplication. When we multiply everything, PQ, and for unit vectors, we usually put a little hat on top of it. We're going to be saying that the unit vector PQ is equal to 1 over root 5, 0 over root 5, which is 0, and they're going to be putting 2 over root 5, which is going to be 2 over root 5. And so this would be how we'd find a unit vector in the direction of PQ. Now, when we want to find out the angle between two vectors, what we have to do is find the dot product of those two vectors and then divide that by the product of the magnitudes of the vectors. So I want to be going ahead and showing you an example so that's easier for you to get. Now, if we want to find the angle between these two vectors right here, we're going to make the one on the left be u, and we're going to make the one on the right be v. Now, cos theta is equal to u dot v over the magnitude of u by the magnitude of v. So we first have to find the dot product of them. So 2 by 3 is 6, plus 1 by 4, which is 4, plus 1 by 5, which is 5. That's going to be 15. Now we need to find the magnitude of each one of them. So the magnitude of u, we're going to square root 2 squared plus 1 squared plus 1 squared, and that's going to be equal to the square root of 6. And now we need to find the magnitude of v. That's going to be the square root of 3 squared plus 4 squared plus 5 squared. Now 3 squared is 9, 4 squared is 16, and 5 squared is 25, so that's going to be the square root of 50. Now we're going to multiply these two magnitudes, so that's going to be the root of 6 by the root of 50. So cos theta is going to be equal to the dot product of u and v, which is 15, over the product of the two magnitudes. So that's going to be root of 6 by root of 50. Now to find out the angle, we're going to take the cos inverse of the right hand side. So that's going to be the cos inverse of 15 over root 6 by root 50. And when you pop that into your calculators, you're supposed to get 30 degrees. One thing I think is very important is for you to understand vector notation. Now, if we have a vector 257, we can also write this as 2i plus 5j plus 7k. And if we have a next vector, 3 minus 4 and 5, we can also write this as 3i plus minus 4j plus 5k. And so when we simplify it, it's going to be 3i minus 4j plus 5k. So we put our x coordinates, or first coordinates, as I, our second one as j, and the third element of the vector as k. So I'm going to be adding these two vectors together, but because I've already shown you how to add, I won't actually be showing you the addition. I'm just going to be using the notation on the result. So to write 5, 1, 12 in vector notation, we can write 5i plus j plus 12k. And so it's very important to note that when you only have 1, then we can just write the coefficient. Now, perpendicular vectors. We actually don't call vectors perpendicular, we actually call them orthogonal. So when we have the dot product of two vectors, if it is equal to 0, then that means that the two vectors u and v are perpendicular. And now the reason this works, or just a little bit of a proof, is if we use our formula, which says that cos theta is equal to the dot product of two vectors over the product of their magnitudes, then we're going to transpose to get the dot product, and that leaves us with the magnitude of u and v multiplied by cos theta. Now cos theta, if we have theta being 90 degrees, we know that the cos of 90 is actually 0, and 0 multiplied by anything is 0. So 0 is going to be equal to our dot product, and so this proves our equation here as well. Now when we have vectors, to determine whether a vector is parallel or not, we look at whether or not it's a scalar multiple of the other vector. So if we have the vector 1, 2, 2 for example, what we usually say is that it's parallel to any vector, and we use a placeholder. I'm going to be using the sign lambda. You could use anything, you could use n, you could use v, any letter, any symbol. So it's going to be parallel to lambda multiplied by 1, 2, 2. So what this is really saying is that once we have a number right here, once we have a real number taking the place of lambda, then it's going to be a parallel vector. And this here is standard math notation. So we're saying this is true when lambda is an element of the real number set. So I'm going to show you an example. If we were to change lambda to 2, for example, then this would be 2 multiplied by 1, which is 2, 2 by 2, which is 4, and 2 by 2, which is 4. Now this vector right here would actually be parallel to 1, 2, 2 because it's a scalar multiple. We could also multiply by 3. If I was to multiply by 3, we'd get 3, 6, 6, and this would also be a scalar multiple of 1, 2, 2, and so it would be parallel. We don't only have to use positive numbers, we can also use negative numbers. For example, if instead of having 3, we had minus 2, we'd put minus 2, minus 4, minus 4, and that would also be parallel to the vector. And our numbers can be floating point numbers as well. So we could have a half, which is 0.5, and if we multiply it, we'd get 1 over 2, we'd get 1 and 1. And this too would also be a scalar multiple of the vector 1, 2, 2. And so it would be parallel. Now I just want to show you why this makes sense. Now look at this graph over here. If we have 2 points A and B, if we want to get from A to B, right, that's going to be 1 AB. But we could also go 2 ABs if we travel the same distance. Or we could go 2.5 AB. Or we could go to 7 AB or infinity AB. We could also go negative AB and go in the opposite direction. This would be negative AB. We could go negative 2AB. This is not drawn to scale. And we can continue doing that for infinity as well. Now, now when we're working on the Cartesian plane, if we have two lines that continue to infinity but are not parallel to each other, then these two lines will definitely intersect at some point. So if we have this line over here and we draw a line like this, it will touch. If we draw a line like this, it will touch. If we draw a line like this, it will always intersect at some point once the two lines are parallel to each other. When we're working in 3 dimensions, however, because we have an x, y, and a z-axis, just because two lines aren't parallel to each other doesn't mean that the lines are going to touch. So on this drawing that I have over here, it's a cube, which is 3-dimensional, and you can see that if we have this vector or this line over here on the face of the cube, if this line was to continue for infinity, it would never intersect with the other line over here because they're just at very different planes or faces in this 3-dimensional space. Now let's actually do a question using all of that information. So the question asks us to determine whether the lines r equal 1, 2, 1 plus lambda minus 1, 2, 4 and r equal 2, 1, 0 plus u, 1, 3, 2 are skewed. Now the first step in determining whether two lines are skewed is to see whether or not these two lines are parallel. A line can only be skewed if the two lines aren't parallel to each other. So to determine whether these lines are parallel, we're going to be looking at the equations for both of these lines. Now, this vector over here only tells us which point to go to. It doesn't actually tell us anything about the direction. The line over here is the one that tells us about direction. It tells us how much we can go of this vector. So once lambda is a real number, this will give us our direction, and over here this will be the vector that gives us a direction as well. So if these two vectors display that the lines are parallel, both of them have to be scalar multiples of each other. So what do we have to multiply minus 1 by to get 1? That would be minus 1. So if we multiply 2 by minus 1, we should have the same thing over here. But 2 by minus 1 is not 3, it's actually minus 2. And 4 multiplied by negative 1 gives us negative 4. But over here we have 2. So these two vectors are not scalar multiples of each other, and that means that they are not parallel. Now, after we've determined that the two lines are not parallel, to find out whether or not these two lines are skewed, the next thing we need to do is find out whether or not these two lines intersect. Now earlier I taught you that once your value out here, your scalar multiple, once that variable is a real number and you add it to the vector over here, you're always going to get a point, some x, some y, and some z that is on that line. Now if we want to find out whether or not these two lines over here intersect, what we are looking for is when r is equal to r. And that essentially means when this vector addition over here is equal to the vector addition over here. So I went ahead and I equated the two of them. And what we're going to do is just put it in some simpler form. So we're going to do some scalar multiplication over here. I want to just put the vector back because we're not changing that yet. So 1, 2, 1 plus, now lambda multiplied by -1 is actually negative lambda. Lambda by 2 is 2 lambda, and lambda by 4 is 4 lambda. Now u by 1 gives us u by 3 gives us 3u, and u by 2 gives us 2u. Now I'm going to make these vectors into 1. I'm going to add them. Now 1 plus negative lambda is going to give us 1 minus lambda. 2 plus 2 lambda, and 1 plus 4 lambda. On the right hand side, we're going to get 2 plus u. We're going to get 1 plus 3u, and we're going to get 0 plus 2u, which is the same as 2u. Now, what we can do is actually to write all of these separately. So using equality of vectors, we know that we can equate all of these. So 1 minus lambda is equal to 2 plus u. 2 plus 2 lambda is equal to 1 plus 3u, and 1 plus 4 lambda is equal to 2u. Now I'm going to make this equation 1, this equation 2, and this at the bottom here, equation 3. We're going to be simultaneously solving this to find out whether or not u and lambda work for all of these equations, because if it does, that would mean that the lines are both intersecting somewhere. So I'm going to be multiplying equation 2 by 2 to give us a new equation, which I'm going to call equation 4. So 4 plus 2 by 2 lambda, which is 4 lambda, is equal to 2 plus 6u, and that's going to be equation 4. Now I'm going to be subtracting equation 3 from it. When we subtract equation 3 from equation 4, what we get is 3, and this is going to give us 0, 4 minus 4 lambda, is equal to 2 plus 6u minus 2u. Now that is going to give us 3 is equal to 2 plus 4u. And that implies that 3 minus 2 over 4 is going to be equal to u. And that is going to be the same thing as a quarter. Now we're going to put this quarter into one of our equations so that we can find the value of lambda. So I'm going to put it into equation 2, and when you put it into equation 2, we get 2 plus 2 lambda is equal to 1 plus 3 multiplied by 1 over 4. This is the same thing as saying 2 plus 2 lambda is equal to 1 plus 3/4, and I want to just bring everything over to one side. So 2 minus 1 minus 3/4 is equal to minus 2 lambda. Now 2, we take away 1 and 3/4 from it, and you're going to be left with a quarter is equal to minus 2 lambda, and then that would mean that lambda is equal to a quarter divided by minus 2, and a quarter divided by minus 2 is the same thing as a quarter multiplied by minus 1 over 2, which is going to be minus 1/8. Now we're going to be putting our values for lambda and u into equation 1 and seeing if these two values satisfy the equation. So 1 minus lambda, which is minus 1 over 8, is equal to 2 plus u, which is a quarter. And we're going to see if this equation is actually true. So 1, we take away minus 1 over 8, that's going to be 1 plus 1/8. Let's just write it like that, 1 and 1/8. And now that should be equal to 2 and a quarter. Now we're going to change it easier to see. 8 by 1 is 1 and 1 is 9. And then 4 2 is 8 and 1 is 9 over 4. Now